the next topic that we are going to look at is that of engine cycles. So, what is an engine cycle? Just to quickly recap what we have done, we have looked at typical components in an internal combustion engine and learned how 4-stroke and 2-stroke engines operate. Now, as I explained to you during the introductory part of this course, the framework for this course is that first we will learn about components operation, right, and then we will do some analysis. So, now let us do some analysis of engines, and in that regard, like using some thermodynamic cycles to do the analysis helps us. Okay. So, how do we analyze engines using what are called engine cycles? What are the various attributes and what are the different ways in which we do that, right? That is something which we are going to learn. So, let us first look at the word cycle, right, and since we are going to look at internal combustion engines, like where we are going to have what to say, conversion of chemical energy into thermal energy and thermal to kinetic energy, we will be looking at what are called thermodynamic cycles, like which naturally fit in. So, first let us ask the question, what is a thermodynamic cycle? So, this is something which you would have encountered in a basic undergraduate course on thermodynamics, right. So, in general, like if you take any system, right, the word cycle means, like the system is taken through a set of states, right, and it comes back to its initial state, right, that essentially completes a cycle. So, a thermodynamic cycle is one where the variables that characterize the state of the system are all thermodynamic variables like pressure, volume, temperature, enthalpy, entropy, internal energy and so on, right. These are typical thermodynamic variables that we encounter. So, we essentially look at these variables and then like take the system through a sequence of states and then we end up at the same initial state, right. So, that is a thermodynamic cycle, right. So, we are going to look at what cycles can be used for analyzing internal combustion engine. And before we go and look at different cycles, we also ask the question that would one classify IC engines, an IC engine, let me put it this way, as an open system or a closed system. So, we would have once again encountered these terms in thermodynamics. What is an open system? An open system is one where you can have both mass and energy transfer, right, between the system and the surroundings. A closed system is one where you can have only energy transfer, but no mass transfer, right, between the system and surroundings. So, if we consider the engine from what we have learned till now, would you classify the engine as an open system or a closed system? Open system. It is an open system, right. So, we have fuel and air coming in, we have energy transfer and then we have exhaust gases also being given to the surroundings. So, let us recall this fact later on. Okay. So, we are going to look at one important class of cycles, like which is what is called as an air standard cycle, okay, and which is what we can reasonably do by using a pen and a paper. Okay. So, if you want to analyze, get some insights into engine performance and so on, we are typically what we do is that like we essentially look at what are called air standard cycles, right. What is an air standard cycle and how is it going to be utilized for engine analysis? So, there are some critical assumptions made when we deal with what are called air standard cycles. The following assumptions are made. So, the first one is the working fluid is air, okay, that is an important assumption, okay, when we deal with the air standard cycle. So, in an actual engine the working fluid is a mixture of fuel and air, right, but when we analyze engines using air standard cycles, now we are going to consider the working fluid as air, okay, that is an assumption we make, right. So, obviously the equations that we get by analyzing engines as air standard cycle is going to be a mathematical model, and as we know a mathematical model is only an approximation of the actual system's performance, right. So, the tighter our approximation or assumptions, that is the less assumptions we make, maybe we expect to move closer to the real system's performance, right. So, in an air standard cycle we assume that the working fluid is air, okay. Second, air is treated as an ideal gas. So, what does this mean? We are essentially going to treat air as an ideal fluid, and we are going to use an equation of state, right, PV equals MRT, okay, for our analysis, okay, that is the ideal gas equation of state, right. So, that is something which we are going to use in this process. The combustion process, okay, that is a process of burning fuel and air, is described by a heat addition process, okay. So, that is another assumption we are going to make, okay. And the exhaust process through which the system is brought back to its initial state is going to be approximated by means of a heat rejection process, okay. So, there is a heat addition process to mimic combustion, and there is a heat rejection process through which the system is brought back to its original state to complete the cycle, right. A heat rejection process is used to restore the system to its original state. Okay, that is another assumption made in this process. And we assume all processes are internally reversible. So, that means that if I go from state A to state B, I can come back from state B to state A in that along the same path, alright. So, that is an assumption, okay. So, these are all approximations, okay, which help us getting this model. And when we want to deal with thermodynamic relationships, right. So, even when we use conservation of energy and other laws of physics, so many times we encounter change in internal energy, change in enthalpy and so on, and we write change in internal energy as the product of the specific heat at constant volume times the corresponding change in temperature, right. Change in enthalpy as a product of specific heat at constant pressure times change in temperature and so on. So, and the specific heats themselves can vary with temperature. So, in this analysis we can either use a constant or variable specific heats, both this method can allow for both, okay, constant or variable specific heats can be used in this process, okay. So, that is these assumptions characterize the air standard cycle. So, as the name indicates, the working fluid is air, we treat air as an ideal gas, and then we are replacing the combustion and the combustion process by a heat addition process, and a heat rejection process is used to bring the system to its original state, and we assume all processes to be internally reversible, okay. Suppose if we consider the working fluid to be both fluid and fuel and air, and we want to analyze the effect of this mixture on engine performance, then we need to study what are called, we need to analyze engines using what are called fuel air cycles. Okay. So, we shall, in this course we shall consider only air standard cycles. Okay. So, obviously as we know, in air standard cycles we can't account for the presence of fuel. So, we would not be able to study the impact of the fuel air ratio or the characteristics of the fuel air mixture on engine performance. So, that is a limitation. So, but anyway we will see what can we learn and in what respect we can use the air standard cycle. Okay. So, the first cycle is the Otto cycle, right. So, this cycle is used to characterize the operation of a spark ignition engine, what we call as a gasoline engine or a petrol engine. It was proposed by Nicholas Otto around 1876, okay, around that time frame is when as we know, Nicholas Otto is a German, right, German automotive engineer who proposed it around 1876. So, what is the motivation, right, behind this Otto cycle? So, if we look at a typical PV diagram, okay, of a gasoline engine, right, and we want to look at the various processes that happen, we typically get a curve which is in this manner. So, P is the cylinder pressure, of course, right, and V is the cylinder volume, and naturally the volume of the cylinder varies between the clearance volume and the total volume. This is the volume at top dead center and volume at bottom dead center, right. Volume at bottom dead center is the total volume, volume at top dead center is the clearance volume, right. So, that is the range of the cylinder volume. So, if we look at the PV diagram of a typical 4-stroke spark ignition engine, let us go through all the strokes. Let us say the suction, we start with the suction stroke. During the suction stroke, the pressure is going to be slightly below atmospheric. Let us consider a naturally aspirated engine. Let us say that I am drawing a very simple curve. Let us say the during the suction stroke the pressure is slightly below atmospheric, right, and then I close the inlet wall and then I start compression. So, the pressure is going to increase, and what is going to happen is that as I come closer and closer to the top dead center, let us say I start the ignition, and then the pressure will increase due to the tremendous amount of heat energy which is released, okay, and then there is an expansion or a power stroke during which the gases are going to push the piston down, and then closer to the bottom dead center I open the exhaust valve, and then the gases are exhausted, and then I come back to the same state. So, if I were to mark the critical points here, so somewhere here let us say I open my intake valve, right. So, this is the intake stroke, then I go here and then I go and start compressing the fuel air mixture, that is the compression stroke, and let us say I start the ignition somewhere here towards the end of the compression stroke, and then there is combustion, and then followed by expansion, and towards the end of the expansion stroke, let us say I open the exhaust valve and this keeps on repeating. Okay, this cycle keeps on repeating. I am just drawing a very simple PV diagram of a 4-stroke gasoline engine. So, how is this simplified and visualized in the Otto cycle? In the Otto cycle, which is an air standard cycle, we are not going to be worried about the constitution of the mixture, right. As I said, we are only going to consider the fluid as air. So, consider a closed piston cylinder combination which has the same quantity of air corresponding to this fuel air mixture, right. Now, what we do is that we are not going to be worried about the intake and exhaust strokes, right, because we have sealed that cylinder and piston, right. So, there is no leakage. So, what we do is that we start with the compression stroke, right. So, let us say we have volume at top dead center and volume at bottom dead center. These are the 2 points. We start with the compression stroke, okay. We are not going to be worried about the intake stroke and the exhaust stroke when we consider the Otto cycle. And before I go to the Otto cycle, please note that if I look at the approximated actual cycle, in this cycle, in this thing, whatever work which I get will be the work output, right. But this area, as we know in thermodynamics, the area of the PV diagram, right, gives me work, either work input or work output, right. But this small area is something where I need to provide energy, that is the engine needs to provide energy, right. And what is indicated by the positive sign is the one which is obtained as output. So, you can see that like the work output obtained during the expansion stroke is used to essentially in a certain sense drive the other strokes, and this area is typically referred to as pumping loss or pumping work, like because that is essentially used to pump the fuel air mixture either into the cylinder or pump out the exhaust gases, right, using that word pump, right. So, that is why it is called as a pumping loss or the pumping work, okay. So, that area, right, which I have shaded in red, okay. So, that is something which the engine should give, okay. So, when I crank the engine before it starts, we are providing that energy externally and even the energy for compression, right. So, till the engine can sustain by itself. So, in the as standard Otto cycle, what we say is that look, I am going to not consider this intake and exhaust stroke because I have a closed volume which is sealed and where the working fluid is only air. I start when the piston is at the bottom dead center, okay. So, what I do is that like I compress the fuel air mixture and then I go to the top dead center, okay, and this is a process in which I keep the entropy constant, okay. I assume that like it is a constant entropy process or an isentropic process. So, the compression process is assumed to be isentropic, okay, from 1 to 2. Then looking at this ignition and the mechanism of combustion, the equivalent heat addition process is assumed to take place at almost constant volume, okay. So, the heat addition process is used to mimic the combustion process and that is assumed to take place at almost constant volume. So, the process 2 to 3 is a constant volume heat addition process, that is how it is approximated, okay. Then comes the expansion. The expansion process is also taken to be a constant entropy expansion process, or what is called as an isentropic expansion process, then the process 4 to 1 closes the cycle, right. So, this is the process where heat is rejected. Once again it is assumed to be a constant volume heat rejection process. Okay, this is how it is visualized and simplified. So, these are the 4 processes. We can immediately observe that we are not going to look at the intake and exhaust. Okay, we will factor that one in later, we are going to see how that affects the analysis, right. So, it is interesting, if you look at the Otto cycle, philosophically we are considering the working fluid as air, and that is contained in a sealed piston and cylinder assembly. So, we are idealizing the system as a closed system, but as we just discussed, an engine is an open system. So, we can see that when we do these engine cycles, like we are going to deal with an approximation of a closed system, but then yet apply it to open systems. Okay, so there is an approximation which is done, but we need to be aware of the assumptions. So, I would stop here for this class, and then we will continue with the Otto cycle tomorrow. We will look at more features of the Otto cycle, and then we will do an analysis. Okay, thank you.